Section 5.3 is conditional probability and the multiplication rules. There's going to be 4 objectives that we look at tonight. The first objective is that of computing conditional probabilities. And I don't remember if I talked about what a conditional probability is yet, so we're going to begin by discussing what that is. If we're told that approximately 15% of adult men in the U.S. are more than 6 feet tall, then the probability of randomly selecting an adult male that's over 6 feet tall in the U.S. it would be 0.15 because 15% of adult men are over 6 feet tall in the U.S. Now, assume that we learned that the selected man is a professional basketball player. We're now not looking at the general population of men, we're looking at a specialized group of men. With this extra information, the probability that the man is more than 6 feet tall becomes much higher than 15% because most of the basketball players in the NBA are over 6 feet tall. So the probability then of selecting a man that's more than 6 feet tall changes when we know that given condition. This is called a conditional probability when you know some given condition. The formula that we use for calculating a conditional probability looks like this, and this is read the probability of B given that event A has already occurred. This vertical line here is what we call a vinculum, is what separates the probability from the given condition. The way that we find this probability is by looking at the probability of both A and B happening at the same time divided by the probability of A. Now, if you'll recall, when we looked at just the general formula for finding a probability, we said that the probability of an event is equal to the number of elements in an event divided by the number of elements in the sample space. Since A is the condition that has already happened, that now acts as our sample space. Now, I'm going to do something that you don't have to recreate on your own, but I'm going to take you through the mechanics of how we transform this formula into something that I think will be more useful to us in the next example that we're looking at. Based on this way of calculating a theoretical probability, I could rewrite this formula as the number of elements in A and B divided by the number of elements in the sample space. This top part right here represents the probability of A and B happening. And then we divide that by the probability of A, which is just the number of elements in A divided by the number of elements in our sample space. Now we end up with what's called a complex fraction, a fraction within a fraction. To simplify these complex fractions, we take the fraction on top and we multiply it by the reciprocal of the fraction that's on bottom. And if you remember fractions, whenever you were in grade school and you first learned about fractions, if you have common factors between the numerator and the denominator, you can cancel them out. And that will then give us an alternative formula for finding conditional probabilities, and that is the number of elements in both A and B divided by the number of elements in A. So you see that A and B become our event, and the number of elements in A becomes our sample space, or acts like our sample space. Any questions about that? So in this example, A would be finding somebody that's over 6 feet tall. I'm sorry, A is that they're in the NBA. B would be that they're finding somebody that's over 6 feet tall. The condition that you're given is what follows this vinculum, and it's what becomes your new sample space, or acts like your sample space, because that event has already happened. On your formula sheet, I would have this as well as this on your formula sheet as 2 different ways of writing the conditional probability, one using probabilities and the other using numbers, because based on the information that you're given, one may prove more helpful or useful than another. You're going to want both. That saves you from having to go through this process every single time of finding these probabilities. I just showed you algebraically how this becomes this. You don't have to reproduce this what's in green on your work ever. You can just stick with what I have written in red and the formula that's in purple. So here's an example problem that illustrates different types of probabilities that we could consider. Consider the following table, which presents the number of U.S. men and women in millions 25 years old and older who have attained various levels of education. This table represents men and women who have various levels of education, and all of the men and women are 25 and over. To help us work these problems, I want to total up the numbers or the count for the men. If we add these numbers up, we're going to get 94 million men and 101 million women, which gives us a grand total of 195 million adults that we're considering. And this is data from the U.S. Census Bureau. In this first problem, we're asked what is the probability that the person is male. If we randomly select an individual, what's the probability that we randomly select a man? Well, using the general probability formula, we know that the probability that we select a man is going to be equal to the number of men divided by the number of people in our sample space. Well, the total number of men here is what? 94, and we know this is measured in millions. We're just going to use the 94 and not call it millions. So we have 94 divided by, and what's our sample space? That's the 195. Now, if you put this in your calculator and round to 4 decimal places, you get 0.4821. And this is the probabilities that we've been calculating so far in earlier sections of Chapter 5. Part B says, what is the probability that the person is a man with a bachelor's degree? Now I'm not looking just at men, I want a man with a bachelor's degree. So you look at your table and find out how many men have a bachelor's degree. So we're looking at man and a bachelor's degree. So that's going to be the number of people that are both men and a bachelor's degree divided by the number of people in our sample space. How many men have a bachelor's degree? 17.5. And you tell that by looking at the row for men and the column for bachelor's degree, and where those two intersect is going to be right here at the 17.5. Then we divide that by 195, and when we put that in our calculator, what do we get?
It says 0.0897.
I'll take it. 0.0897.
Why did you put man and bachelor's
Because it has to be a man with a bachelor's degree, so I need it to be both a man and have a bachelor's degree. Because this would be men with an associate's degree, men with some college or no degree, men with advanced degrees.
Like right?
Yes, this is still the old stuff. Now we get into the new stuff. Part C says, what is the probability that a person has a bachelor's degree given that he is a man? When you see these words right here, given that means a conditional probability. The way that you read this right here, the way that you would express this in words is the probability of A given that B has already occurred. This is how you would read these symbols here for the conditional probability. In this problem, we're told what's the probability that the person has a bachelor's degree given that he is a man. The way I would write this in symbols is what's the probability that they have a bachelor's degree given that he is a man. Based on the formula that we had earlier, we're going to look at the number of bachelor's degrees and men divided by the number of what? Man. Remember, I said the condition that you're given becomes your new sample space. And that's because we had raw numbers here and not probabilities. I wanted to show you how to write this conditional probability formula using the number notation. So this would be the number of A and B divided by the number of B. Whatever follows that vinculum becomes your new sample space. So man here is the condition that we were given, and that becomes what I put in the denominator for the probability. Looking at the table then, how many people are men and have bachelor's degrees? That's still 17.5. Now our sample space is the total number of men. What's the total number of men? 94, and when we put that in our calculator, what do we get? So knowing the condition that we had that we were selecting a male changed the probability of selecting somebody that had a bachelor's degree. Do you see the difference between these three probabilities? The first one is just a straightforward probability. The second one is the probability of a compound condition. Both of these things had to happen. The third one is a conditional probability. This is new. Can we try one more? Okay, you want to try one more, so I'm going to make up another one. So for D, I'm going to ask it like this. Alright, so I've made this question up. It's not in your notes. So let's look at this. This is very similar, worded very similar to C, but what I want to point out is we're going to get a different answer. So this is asking us, what is the probability that the person that we randomly select is a man, given that I've now restricted myself to somebody that already has a bachelor's degree? Do you see the difference between C and D, what I'm asking? What I changed was the condition. As a matter of fact, I just switched these two. Do you think that these will have the same probabilities? No, they're not going to. Now the top number will be the same. The number of men with bachelor's degrees hasn't changed. BA is my abbreviation for bachelor's degree. My sample space now will be the number of people that have bachelor degrees. So we still know that 17.5 men have bachelor's degrees, but now we need to know the total number of bachelor degrees that there are. So if we add 17.5 to 19.2, what do we get? 36.7? Now what's 17.5 divided by 36.7? Okay, I'm trusting you on the numbers because I didn't work this out in advance. So the order matters here on these conditional probabilities. That's another point that I want to make. The probability of A given B most likely will not be the same as the probability of B given A. The given condition is what has to go right here in this second position. That becomes your sample space for the probability, because that condition has already happened. Objective 2 is the general multiplication rule. I don't think we've talked about the multiplication rule at all yet, have we? Okay. So objective 2 is to compute probabilities by using the general multiplication rule. The general method for computing conditional probabilities provides a way to compute probabilities for events of the form A and B. If we multiply both sides of an equation by the probability of A, then we obtain the general multiplication rule. So I take that formula for conditional probability and I multiply both sides by the probability of A. Remember, here's the probability for B given A is equal to the probability of A and B divided by the probability of A. Just doing a little bit of algebra here. If I were to multiply this side of the equation by the probability of A, multiply this side of the equation by the probability of A, these terms would cancel out and I would have the probability of A and B equals the probability of A times the conditional probability. That's how this formula was created from the conditional probability rule. You don't need to know how to do this. I just wanted to explain to you where that formula came from. This is how this conditional probability came into being. And we get this other one down here because we also have, I could write my conditional probability like this or like this. So if I have my probability written like this, then I would multiply both sides of the equation by the probability of B, and that gets me this form for the conditional probability. These you need to put on your formula sheet. Let's look at an example where we would use this general multiplication rule. Among those who apply for a particular job, the probability of being granted an interview is 0.1. Among those interviewed, the probability of being offered a job is 0.25. Find the probability that an applicant is offered a job. So getting a job offer involves two events, an interview and the offer. So one way I could write this is the probability of getting an offer means that you got interviewed and you got the offer, because you can't get the offer without being interviewed. So that's going to be equal to the probability of getting the interview times the probability that you get the offer given that you interviewed. That's writing this out using words. Does that make sense? Well, we were told in the problem that the probability of getting the interview to begin with is 0.1. The probability among those who interviewed, that means that you had to have interviewed, given that you interviewed, the probability of getting the offer is 0.25. And when we multiply these numbers together, that gives us 0.025. So there's only a 2.5% chance of getting the job, or getting the job offer. Alright, now this general multiplication rule is what we use when we have two dependent events. You getting the offer depended on how you did in the interview, didn't it? Those would be dependent events. Objective 3 deals with what we do if we have independent events. Objective 3 is computing probabilities by using the multiplication rule for independent events. So let's talk about what an event looks like if it's independent. Two events are independent if the occurrence of one does not affect the probability that the other event occurs. That's about as simply as I can put it. If two events are not independent, then we say that they're dependent. I could use a formula here to illustrate this point. If the probability of A given B equals the probability of A, then A and B are independent. Or, switch the order of the letters, if the probability of B given A is equal to the probability of B, then A and B are independent. If the probability of one event, in this case A, doesn't change if you know that something else has already happened, then we would say that these two things are independent. In this next example, I'm going to present you with two scenarios. One of these is independent, one of them is dependent. So let's read the two scenarios and see if we can figure out which is which. The first one is a college student is chosen at random. The events are being a freshman and being less than 20 years old. The second scenario is a college student is chosen at random. The events are born on a Sunday and taking a statistics class. Out of these two scenarios, one of them is independent and one of them is dependent. Which one do you think is independent, one or two? The day of the week that you're born has no bearing on what classes you take. However, most freshmen come to college right out of high school. You're usually anywhere from 17 to 19 when you graduate high school. So you would be less than 20 if you knew that you were a freshman. Yeah, if that given condition changes the probability of the first thing, then it's dependent. So here, if I asked you what is the probability that you're let's leave it like this, under 20, less than 20, given that you're a freshman, that probability is going to be very different from the probability that you randomly select a person that's under 20. This probability is going to be much higher. They're not the same. However, the probability that you're born on a Sunday, given that you take a statistics class, that's probably going to be the same as the probability that your just randomly selected person is born on a Sunday. Because we don't restrict enrollment in statistics to people who are only born on Fridays or born on Tuesdays or whatever. Does that make sense? These are independent because knowing that somebody's taking a statistics class isn't going to change the probability of the day of the week that they're born on. Does that help clear things up? If knowing this condition changes the probability of this thing, then they're dependent. That's what I tried to explain or get across up here. If knowing this condition doesn't change the probability of the event without the condition, then they're independent. The multiplication rule for independent events is easy. We like this rule. Because of this fact right here, the fact that this conditional probability, that condition doesn't change the probability, we can easily go from the general rule. Let me write down the general rule again to help you remember. The probability of A and B is equal to the probability of A times the probability of B given A. If A and B are independent, this condition isn't going to matter, and we just get the probability of A times the probability of B. And that's where we get this multiplication rule for independent events. It's easy to find the probability of two things if you know that those two things are independent. So let's look at this problem now where we're asked to find the probability of a series of events. According to the recent figures from the U.S. Census Bureau, the percentage of people under the age of 18 was 23.5% in New York City, 25.8% in Chicago, and 26% in Los Angeles. If one person is selected from each city, what is the probability that all of them are under 18? So here's the percentage of people in those cities that are under 18. What I'm asking you is, what's the probability that you select one person from Chicago, one from New York, one from LA, and then that they're all under 18? The first thing you always want to consider is, are these events independent? My events here being selecting one person from each city. Yeah, because people from Chicago, New York, and LA are all independent of each other, right? So what I want to find now, because these are independent, is the probability that I randomly select someone from New York and Chicago and Los Angeles, and that's going to be equal to the probability of randomly selecting someone from New York who's under 18 times the probability of selecting someone from Chicago who's under 18 times the probability of randomly selecting someone from LA who is under 18. Because these events are independent, it makes the multiplication very easy. I was told that 23.5% of New York City is under 18, so what's the probability that I randomly select someone from New York who's under 18? 0.235. And the probability that I randomly select someone from Chicago who's under 18? 0.258. And LA, I'll just write it 0.26. Get out your calculator and we multiply these numbers together and round this answer to 4 digits. What do we get? Okay. The next thing we were asked is this an unusual event? Do you remember how we determined if something is unusual or not? I'll tell you. Unusual events have a probability less than 0.05. So is this an unusual event? We have 0.0158. That's definitely less than 0.05. 0.05 is an arbitrary cutoff point that we've just accepted as a working hypothesis here. And it's pretty universally accepted across all the different textbooks that I've been exposed to. Sometimes we are interested in finding probabilities when we do sampling either with or without replacement. So when we sample 2 items from a population, we can proceed in one of 2 ways. We can either replace the first item drawn before we pull the second item, in which case that's sampling with replacement, and that is an independent thing. So sampling with replacement is independent. Or if you wanted to find, let's say that I'm drawing from a deck of cards and I wanted to know what's the probability of selecting heart and a queen. Well, if I draw my first card and I put it back in the deck, then the probability of selecting another card is going to be the same because the sample space hasn't changed. It's still 52 cards, right? But if I don't put that first card back, I'm sampling without replacement, in which case I'm going to have a dependent situation because the number of cards in the deck has now changed, and that means that I've got dependence going on. There is an exception to this when you can sample without replacement and still assume independence. We like assuming independence because the formula for finding probabilities is much easier if we can assume independence. Here's the exception rule. If your sample is less than 5% of the population, then you can assume independence. So for example, if you're working at M&M Mars and they make like 8 million candy bars in a shift or whatever, and you're doing quality control and you go pull 100 of them off the line to weigh and measure and stuff, you can assume that each of those bars are independent because the 100 that you pulled off are less than 5% of the 8 million that they produced. You can assume independence if your sample is less than 0.05 times the population. Less than 5% of the population. And like I said, we like assuming independence. The last objective in this section is probably the most confusing, but once you get it, it won't be so bad. Objective 4 is computing the probability that an event occurs at least once. When you see the words at least one, I want you in your mind to think of using the complement. Let me give you a quick reminder of what I mean. The last thing that we went over, I think in section 5.2, was the complement of events, and we said that the probability of an event is equal to 1 minus the probability of the complement of the event. Remember, an event and its complement together form the sample space. If this right here represents my event E, everything outside of that in my sample space is going to be E complement. It's in the sample space but not in the event. If the probability or the area of this entire region is 1 and I know the area that's shaded in blue. If I do 1 minus that area in blue, I've got the area in red if the area in red represented the probability of my event. Okay, to find the area of this region that's in the red circle, all I got to do is find the region in blue and then subtract that from 1 if the total area of the rectangle is 1. Well, when we see the words at least one, the complement of at least one would be none or all, depending on how you worded things. There's only one way to get nothing, and that is to have nothing of something. But at least one means you could have 1 or 2 or 3 or 4, and there's a whole bunch of different ways to do that. The easiest way to calculate the probabilities is by finding the probability of the complement. Remember that the complement of at least one event occurs is that no event occurs. To compute the probability that an event occurs at least once, we're going to find the probability that it does not occur at all and then subtract that from 1. We're going to do this the easy way first, and then I'm going to come right beside it and show you the hard way to calculate or to work this problem from a straightforward head-on approach. In this example, we're told that items are inspected for flaws by 3 inspectors. If a flaw is present, each inspector will detect it with a probability of 0.8. So the probability that they detect the flaw is 0.8. What's the probability that they don't detect the flaw? 0.2, because you've only got 2 choices. You detect it or you don't. If the probability of detecting it is 0.8, the probability of not detecting it or making a bad call is 0.2. The inspectors work independently. There's your key word. We're looking at independent things. This is a good thing. That means that probabilities are going to be easy to find. If an item has a flaw, what is the probability that at least one inspector detects it? So our event here is that at least one inspector detects the flaw. What would be the complement of our event in words? None of the inspectors detect the flaw. Notice, here's your event, at least one. Here's your complement of the event, none. I said the complement of at least one is none. Detecting the flaw is what we're talking about. Because all 3 inspectors are independent of each other, that means that the probability of the complement of the event will be equal to the probability that the first one fails to detect the flaw, the second one fails to detect the flaw, times the third one failing to detect the flaw. Our inspectors are independent, so I'm able to multiply like this. The complement means that they failed to detect the flaw. None of the inspectors detect the flaw. What's the probability that the first one failed to detect the flaw? The probability that they detected is 0.8. What's the probability that they failed to detect it? 0.2. And the second one? 0.2. And the third one? 0.2. And we multiply those numbers together and we get 0.008. So this is the probability that they failed to detect. Now is where we use the complement rule. The probability of our event is equal to 1 minus the probability of the complement of the event. So the probability of our event is 1 minus 0.008, and that's going to be 0.992. Now this is how you would find the probability using the complement. What if I didn't want to mess with the complement? I just want to look at my event. Well, I've got to consider every possible way that I could have my event, at least one of them good. So I'm going to, for the other approach, you don't have to write this down. As a matter of fact, I recommend you not write this down because I'm going to model for you the way you don't want to work this problem. And when I model it for you, hopefully you'll see why you don't want to work it this way. So I'm going to let G be detecting the flaw. And I'm going to let B be failing to detect the flaw. If you want to know why I picked those letters, G for a good call, B for a bad call. To get at least one inspector to make a good call, I could have a bad call, but then one of them's got to make a good call, right? Or I could have the first one make a bad call, the second one make a good call, the third one make a bad call, or good, bad, bad. That's at least one making a good call. Either the first, second, or third one's going to do it. Now this is also at least one. The first two guys could make a good call, and the last one makes a bad call. This is also at least one good call. And this. But this is also at least one good call. They could all three make good calls on this, right? So what I would want to do here is find the probability of this plus the probability of this plus the probability of this plus the probability of this, and you get the idea, so forth and so on, right? Now, the probability of making a bad call we said was 0.2. So that would be 0.2 times 0.2 times 0.8, because that guy made a good call. And when I multiply 0.2 times 0.2 times 0.8, I get 0.032. And I am going to need somebody with a calculator to double check my arithmetic for me. I know if that number's right, this number's going to be right as well, because multiplication commutes. That's still 0.032. And same thing here, good call times bad call. Because these are independent, I can multiply like this, right? All three of my inspectors we said are independent of each other. Now the probability of good, good, bad is going to be 0.8 times 0.8 times 0.2. Well, that's 64 times 2 is 128, so that's 0.128. Is that right? And I'm okay on this one. It's the third one, the last one that I'm going to need the calculator on. And this one's 0.2 times 0.8 times 0.8. And that's 0.128. 8 cubed, I'm not real sure of though. This is 0.8 times 0.8 times 0.8. And what do we get for this one? All of these different things represent different ways of getting at least one good call. Because I could do this or this or this or this. Do you remember what we did in 5.2 when we saw the word or? Or means we added the probabilities together, right? If I add all of these probabilities together, guess what I get? This is a much safer way of working the problem, because what if you didn't consider all of the possibilities here? Or what if you had 10 inspectors and you wanted to know the probability of at least one of them making a good call? As the number of inspectors increases, this problem gets out of hand really fast. The only way to work a problem when you have more than 3 of these things to choose from is to use the complement. The probability of an event is 1 minus the probability of the complement, where the complement would be none of the thing happening. And there's only one way to get the complement, and then we subtract that probability from 1. On your formula sheet, I need you to make a note that if you see the words at least one, it means use the complement. If you read the words at least one on a homework question or on a test, your mind should immediately think use the complement. What I have written in green here is the formula for finding a probability with the complement. Any other questions about anything? You see why I don't like this method? You probably won't like it either, especially if I had 10 inspectors instead of 3. But it also verifies that the complement method works. So we went over several things tonight, and I'm not going to take the time to read them all, but I do want to point out a couple of things rather quickly. The easy way to determine whether events are independent or dependent is to check the conditional probability and see if knowing that condition changes the probability of the first thing. If this happens, then we have independence. And also, if you see the words at least one, I want you to think complement. And this wraps up section 5.3.